What's the problem?
Probe 1, a group of the Perseus meteors have separated from the main body and are now heading directly for Geosat 4. We'll have to boost the satellite to a higher orbit.
Roger, Capcom. We copy.
Hold it, Charlie. If they move the satellite, we'll lose communication with Capcom, with Earth, with everything.
Capcom. How will we transmit if you change the satellite's position?
We've calculated that Geosat 4 will be safe at an orbit of 4,600 kilometers. We'll reset our annual transmission at
Looks like we'll have to figure this one out ourselves, eh, Charlie?
Put it up on the screen, Ed, and let's begin our trig calculations.
In the last program, we saw how trigonometric ratios are used to calculate the sides and angles of right triangles. Knowing one of the acute angles and the length of one side, we can find the unknowns. The sine of 50 degrees equals the opposite side divided by the hypotenuse, or y over r. But there are two unknowns, so the sine ratio won't do. However, using the cosine ratio, we can find side r. The cosine of 50 degrees equals adjacent over hypotenuse, or 4,600 over r. A calculator gives the value of cosine 50 0.643. Since 4,600 over r and 0.643 are both equal to cosine 50, then they must be equal to each other. Multiplying both sides by r, and then dividing by 0.643, we have the length of r. We can now find the length of y using the sine ratio. The sine of 50 degrees is y divided by 7,156.3. And sine 50 is 0.766. All we have to do is solve the equation for y. So probe 1 must reach an altitude of 5,481.7 kilometers to pick up Geosat 4. So far, we've defined trig ratios to work with right triangles. But what if Geosat 4 were here or here? No obvious right triangle. But we can create a right triangle by using the Cartesian plane. Let's review the coordinate system. The coordinates of point P, X, Y can be found by dropping perpendiculars to the X and Y axes and counting out. This point is called 5, 2, with the X value first. The coordinates of the point are known as an ordered pair. Now let's place an angle on the plane, with its initial arm lying on the x-axis, and the terminal arm sweeping up in a counterclockwise direction. The terminal arm can lie in any of the 4 quadrants. Let's work with angle theta. Theta's terminal arm passes through point 35. The terminal arm is sometimes shown extending beyond the point. However, for simplicity, we'll cut off the extra and also eliminate the grid. If we drop a perpendicular to the x-axis, we create the necessary right triangle. The perpendicular is PA. The length of OA is 3 units, and PA 5 units. Using the Pythagorean theorem, the length of OP can be found. .8. For any point xy, r equals the square root of the x-coordinate squared plus the y-coordinate squared. We can also find the trig ratios for point xy. An imaginary triangle is created with sides x, y, and r. The sine of angle theta is opposite over hypotenuse, or y divided by r. The cosine of theta is adjacent over hypotenuse, or x over r. And the tangent of theta is opposite over adjacent, or y over x. So, by knowing the x and y coordinates, we don't have to construct a triangle to establish the trig ratios. In this example, the terminal arm passes through point -4, 3. The length of r equals the square root of x squared plus y squared, or the square root of -4 squared plus 3 squared. With r equal to 5, we can now find the values of the trig ratios. If the terminal arm passes through the point -2, -5, r equals the square root of -2 squared plus -5 squared, which equals the square root of 29, or 5.4. And the trig ratios are as shown. This method works for a terminal arm in any quadrant. We use the x and y coordinates to find the value of r, and then substitute the values into the trig ratios. So, there it is. We can now find the sine, cosine, and tangent ratios for any angle between 0 and 360 degrees.
And record that information. We're going to need it to reach the black hole at the center of the galaxy.
Oh, well, yeah. Okay, Charlie. But gosh, Charlie, it spins just like our galaxy.